will be 50% of the final weight. Okay. Any other question? Okay, if you have no question, then we can just start the lesson for today. So for today, it will be introduction to deep learning. Okay. To be started, we should understand the definition of deep learning. What is deep learning? Deep learning is a class of machine learning algorithm that use multiple layers to progressively extract higher level feature from the raw input. Right. If you see the figure I have in the slide, you will see that deep learning is a class of machine learning algorithm, and the broader domain than the machine learning is artificial intelligence. For artificial intelligence, it refers to any techniques that enable computer to mimic the human behavior, right? So it could be a robot that can do something, that can react to the environment, right? And for the machine learning, is the ability to learn without explicitly being programmed, right? For artificial intelligence, you might be some, AI that is that rule-based system where you define the rule, and then the AI will follow the rule, right? But for machine learning, we focus, it is a subtopic of artificial intelligence that refer to the ability to learn without explicitly being programmed. Usually you train the model by using the data, and the model can learn, extract the pattern from the data, right? And deep learning is a subtopic, a subclass of machine learning topic. So it has the same purpose of extracting the pattern from the data, but the specific model in deep learning are neural network. Okay. Why deep learning? The traditional machine learning method require manual engineering, which depend on the domain expertise and experience. I expect that you already study the machine learning class. Is this correct?
Yeah.
Is that correct for everybody, that you already study the machine learning class? Could you please raise your hand? Let me check the percentage. Okay. Okay, so it's more than half. So I assume that the other just didn't pay attention to the question. Okay. So for traditional machine learning methods, for example, when you do the classification algorithm, let's say SVM, and in order to do classification algorithm, you need to have a data set, a labeled data set with where the sample consists of two information. a pair of information, the data feature and the label, right? And usually for the feature, you have a lot of feature, and usually you can do some kind of feature engineering to improve the quality of the input. And with that feature engine, you can somehow boost the performance of the system, right? And if you apply the machine learning to the image processing problem, let's say do the image classification, right? The idea is to be able to have models that can classify the image to be a dog or image to be a cat, okay, right? And usually if you apply the classification algorithm, and you normally people will do some kind of a feature engineering from the image. You extract the key point, you extract the key information from the image, right? And then from that you apply the SVM model, right? So somehow the feature engineering, when you do traditional machine learning methods, is very important, right? And it really have a high consequence on the final performance of the model. Okay, and to do good feature engineering, it will depend on the domain expertise and experience that you have, right? For deep learning, deep learning can allow you learning the feature representation from the data automatically. And let's say that for deep learning, you can have end-to-end model that you can put the raw input in the other side, and you can have the output label at the other side. And the model, the big model you have, we learn the feature representation itself, right? So you can say that, okay, you are free from the feature engineering, right? The model will learn the feature, the good feature, the good representation for the data, and then make the good classification output. You have the image here where it depicts some kind of feature learned in the neural network at different level, a different layer. This is so it can learn the low-level features such as the contrast, the some kind of the egg in the image, right? And then you have upper mid-level feature such as the features that describe some property in the face, right? And you have the high-level feature where it really can represent the face, okay? So I must say that right now the deep learning is very popular, right? And you can see that it is discussed like almost everywhere, from industry to academia, right? But the neural network has been proposed back several decades ago, but why it is so important right now? There are three components that make the let's say the popularity of the deep learning. One is the data, the big data we have right now. The second one is the hardware, right? The third one is the software. So for the big data, right now people have more and more big data set, right? You see we have the ImageNet that have a like I'm not sure about the correct number, but it's have a lot of image, and you have 1,000 classes. Okay. For the hardware, at the moment, you have the CPU, the graphic processing unit that can do massively parallelism. Okay, and it can be easy to leverage this GPU to do the computation on the neural network. And the third one is the software. In the past, when you do neural network, you have no or little library that support the creation and training of the neural network. Right now, what do you have? You have the TensorFlow, you have PyTorch, you have Caffe, you have EmigNet. A lot of library and framework that can facilitate the way you implement the network and train and monitoring the network, right? It is so easy for you right now. For example, if you use Keras or PyTorch, you can just define a neural network, a very big one with just a few lines of code. That's very important to make the deep learning to be very popular for the moment. Okay, so now we can recall, try to discuss a little bit about some few concepts on machine learning that are related to the thing that we will study in this course. First is supervised learning. So in supervised learning setting, what you have is you have labeled data, right? So for the data, you have a pair. Example is a pair. One is X and the other one is Y. X is like the feature, the data property, and Y is the label, the output, the expected output for the that data sample. Okay. And in supervised setting, you will try to build a model. Actually, it is to try to find out the f, the optimized f function that can approximate the data set. Okay, the training data set. Okay, so whenever you have the optimized function f, then you can try the f with the new data, and you will have the prediction. So this is like the output of the learned model. Okay. So yes, the next thing you will I will discuss with you is the learning process in machine learning. So usually for machine learning, you start with the data, and they are usually historical data that was collected during the execution of some system. And for that data, you divide the data set into three subsets. The first one is the training set, and the second one is a validation set, and the third one is a test set. Okay, so for the training set, you will use this data set to train the model, right? To let the model learn from the training data so that it can approximate the output, the expected output from the input. Okay, and you use a validation step to do the model optimization, such as the parameter tuning, right? Like you training the hyperparameter, such as the it depends on the specific machine learning algorithm that you choose. For example, it is SVM, then it could be the kernel or whatever, right? And after you have the best model that perform with the highest score for in the validation set, that you can test the model with the test set. Okay, and in either case, you guys come up with the retrain the model again with new data, or you are not satisfied with the model on the test set, then you can come back and work on another model, for example. This is an illustration for the train and test set. This is a universal set we have, right? And from the data acquisition, that is where you collect the data, then you will have a training set. In the training set, you have the label associated with example. It's the, for example, it is first class and it is second class, the data set, right? And this training set will be used to train the model, and after having the model, you can use that model on the on production, and that means you use the model in an observed set, right? And you can measure if the model performs well on the test set or not. Talking about the quality of the model, I would like to remind you about the concept of bias and variance. Bias is defined as the difference between the average prediction and the correct value of the data. And variance is defined as the variability of the model prediction for a given data point or value which tells us spread of our data. So take a look into the figure we have. So in this case, right, in this case, it depicts the situation where we have the model that produce low variance and low bias, right? And in this case, you have the model that produce low bias but high variance. Okay, so the bias is calculated from the average prediction and the correct value of the data. Okay, so you see here the mean, the average prediction is very close to the expected outcome, right? So in this case, you see the prediction is spread over different location, but the mean, the average prediction is somehow still here, so it's very close to the correct value of the data. So in this case, you have low bias, right? But talking about the variability, this situation you have high variance. Okay, so in this case, we have high bias and low variance. The average prediction is very so the average prediction is very different from the expected outcome. Okay, but the variance is very small, right? All of the prediction is somehow very close to each other. Okay, so in the last situation you have here is a model that produce very high bias and also high variance, right? Of course, in this case, you see the average prediction is somewhere here, right? And the variability is too big, right? Okay. And from the bias and variance, you may say that the model is underfitting or overfitting, or the model is good, right? In the underfitting situation, the model is too simple to represent the property of the data. That's the idea about underfitting. And that means that you have a high bias and low variance, right? You have high error on the training set and also high error on the test set, right? So if you plot the error rate for the model, and you see that this is a underfitting region, right? This is a score for the test set, and this is score for the error set. You see the error is very high for the both training set and test set, right? And if this very high bias, then you see this is an example. The error is very high. That means the model could not learn from the data, right? It is too simple to learn to model the property of the data, so that how the output is very high bias and low variance, right? In the case of overfitting means that the model is too complex. That is, this is too complex, so that it's also learned from the noises in the data. By overfitting, the model have low bias and high variance, right? And it have low error on the training data set, but very high error on the test set. So this is a region for overfitting. You see that the model perform somehow very good on the training set. So it learned everything, even the noise from the training data set, and it could not derive well for the test set. So that's the idea of overfitting. So you see, this is one illustration for the overfitting situation. This is the training set, right? And the model learn perfectly for the training set. It even learned a very non-linear separation between the two classes. Okay, but of course, I mean, this is too much too specific for the training set, and you see it cannot derive for the test set, so that you have a very high error for the test set, right? And yes, so the case one is to have a good balance somewhere here, where you have low error on the training set and also low error on the test set, right? So this is the good scale where you have the model that can learn to separate the two classes, but it's not very specific to the training set, right? It can, how to say, doesn't take into account the noises, right? In this example, the noise is somewhere here, right? This is a noise. This is a noise, right? Okay. Do I have any question for this moment? Do I have any question? Okay. Okay, no question. Then we can move on. Okay, so now we will study about artificial neural network. And I expect that you already have this lesson in the machine learning class. Is this correct? Is it correct that you already study about the artificial artificial neural network in the machine learning class? Please raise your hand if you already took the lesson. Okay, 22. Okay, right. Very good. So we can move fast. So artificial neural network. Let's start with the human brain. And you see in the image, it is a illustration of the brain cell, the neuron in our human brain. It is said that the human brain is made up of many interconnected neurons, and the neuron receives signal from other neurons through synapse, right? It's like the connection between the two neurons, okay? And when a neuron receives enough signal within a few milliseconds, right, then it finds a pulse that finds its signal, okay, right? So the neuron could be some kind, okay, the function that receive the input, and then upon some condition, enough signal, it will find the output signal, okay? So that is the way that the neuron and our brain work, right? So each neuron is a perceptron, and perceptron, this the structure of the perceptron, where, sorry, I check the slide. Oops. Okay, so this is a perceptron. So for the perceptron, you have a different component. It is the nucleus, okay, it's kernel of the neuron, where the dendrites, it is like uh, the input of that perceptron, right? The input channel of the perceptron, right? And then you have the axon. This is this is used to carry the input away from the cell body, and then you have the branch of axon that have an axon terminal, and this where you connect to other perceptron, right? This is natural neuron. You have a perceptron model that was proposed a long time ago in 1957 from Rosenblatt, France. And in that perceptron model, you have a number of input signal, x1, x2, xn, and you also have the bias, the x0. And that perceptron first calculate the net input. It is equal to the weighted sum of the input and the corresponding weight, okay? And that will find a fire pulse which activate if the weighted sum of the input bias T is not negative, right? So basically, after the net input, this is like the input to the activation function, activate something, output something, right? And this function is simple, like you will output 1 if the net input is bigger or equal than 0, and it will output nothing in the other case. Okay. So for the perceptron, the net input is usually calculated by a linear function, as in the example we have, right? So in this slide, I just want to remind you about the importance of the bias, right? If you use the perceptron to do the a very simple two-class classification, let's say you have the different number of points with two labels, black and white, and you want to use the perceptron to do the classification. And in this case, you see that when we have no bias, then every sorry, every the net input will be every net input, right, will be a line that cross the zero zero. Sorry, I forgot the word in English, but it's across the how to say. Okay, so sorry, maybe I too confusing right now. So if you have the bias, right, and then the perceptron can represent a function, a linear function that have no constraint on the that specific. Okay, let me check a little bit about how to call that. Okay. So is this like the origin of the X? Is that correct? Do you know how to call that specific point? Okay, it's the origin. Okay, right. Sorry, this is first time that this is got in English, so something that some concept that I really don't know how to name it in English. Okay, so yes, so if you have no bias, then the net input will be the line that always cross the origin of the X, right? And in this case, you cannot use that line to classify the two class. Okay. And when you have the bias, then you see now the line could be everywhere, right? So in this case, you can, right? Okay, so now we discuss the activation function. So first activation function that you have is a hard limiter function. So in this function is very simple, where it have the positive output value 1 for every v bigger and or equal than 0, and you have 0 in the other case, right? And this function is actually having a threshold, right? It has all the properties that it is discontinuous. The value of the function is not continuous at the threshold. Okay, it is a threshold, and before the threshold, the value is 0, and just after the threshold, you have the value 1. So that is discontinuous. Okay, and also for the derivative of this function, it is also discontinuous. This hard limiter function. Yes, okay, so you have other activation function is namely the threshold logic function. So the difference is range between the lowest lowest output and the highest output. So you have this is a lowest limiter, and this is the highest limiter, right? And in between you have the the value is a variation from the lower limit to the higher limit, right? And it's actually a linear function, and you see that it is set of the threshold logic function. And in this case, you have a contiguous function, right? Continuous function. Sorry, I used the wrong keyword. Continuous. Right. And for the derivative, because it is you still have threshold, and that will make the derivative to be discontinuous. Okay, it is the threshold logic function. You have the third function, the sigmoid function. It is a very popular activation function in the past. You have the output from the sigmoid function to be in the range from 0 to 1. It is continuous, and of course, for the derivative is also continuous, right? So it's very beautiful. And the other beautiful thing about the sigmoid function is it is very easy to differentiate, like the derivative, right, of the sigmoid function, and it actually represents by itself, and then 1 minus itself. Okay, so easy for you to calculate. You have other activation function as well, such as the piecewise linear function, the tangent function, the rectified linear unit function. Okay, you will study more about the activation in the lesson number 3, just after the lesson on the convolutional neural network. Okay, so now you will be discuss on the importance of the activation function, right? Before I show you the information, the importance of the bias, and now I show you the importance of the activation function. Without the activation function, the output of the net input is a linear function, right? So a linear activation, sorry, the purpose of using the activation function is to introduce a non-linear layer into the neural network, right? If you have no linear activation function, or if you use a linear activation function, then the output will be always a linear separator, no matter how large the network is, right? You see, this is one of the representation for the linear function, that it cannot, how to say, represent the separation between the two classes. Okay. So if you introduce a non-linear activation function, then you may have a chance to approximate complex function. So for example, by using non-linear activation function, you can have this very complex curve that separates the two classes. Okay. So basically, if you compare the artificial neural network and the brain, you may see that they are a lot similar to each other, but the biological neural network have a more complex connection. In the case of artificial neural network, ANN, usually we are working with the network where the neurons are organized into layers, and this kind of organization is used to increase the computational efficiency through parallelization. This is the way I want to show you about the layer, right? In the biological neural network, I mean, you can see that the neuron can be a very complex connection, and in the ANN, you can classify the neuron into layer, and it is just to make the network to be simpler and make it to be efficient in a parallel computation. The ANN is said to have the ability to learn, to recall, and to derive from learning data, right? It can learn and it can recall because, I mean, from the observed data, it can learn and predict the correct expected output, right? And it can generalize because you can put the unseen data to the trained neural network, and then the neural network can predict the output, and that predict output is somehow is the same as the expected output, right? The capacity of an ANN depends on several criteria. First is architecture or the topology of the network, right? So in the next slide, we will study some common neural network architecture, right? Okay, besides the topology, the architecture of the network, the capacity of an ANN also depend on the input and output characteristic of each neuron, right? And for the So it's talking about this line, information. I might refer you to the neuron to the number of output and the activation function of each neuron. The other property that impact the capacity of the RNN is a learning algorithm, right? And also the learning data. It's easy to understand because if you have good data, then it can be easier for the model to learn, and the model will be somehow better in terms of performance, right? If you have a you have good learning algorithm that it can you can have a big difference with the same input training data. Okay. Okay, so for the RNN, the architecture of an RNN is defined by the number of input and output signal, the number of layer, the number of neuron in each layer, the number of connection for each neuron, and how the neuron in a layer or between layer connect with each other, right? But in all of the case, the ANN must have an input layer, an output layer, one or no or more than one hidden layer. So it is in the architecture of the neural network in general. So in the image, you have an example of an ANN with one hidden layer. Okay, this is a hidden layer. You have just one hidden layer. Okay, you have 3 inputs here. Okay, this is the bias. Okay, you have 2 output. Okay, and in total there are 6 neurons, 4 on the hidden layer and 2 on the output layer. Okay. So the definition of the layer in neural network, a layer of neuron in an artificial neural network is a group of neuron. A hidden layer is a layer between the input layer and the output layer. In the hidden layer, the hidden node do not interact directly with the external environment. Of course, when I'm talking about the external environment here, I'm talking about the environment of the neural network, right? So that means that the hidden layer only to interact with the input layer and other hidden layer, and also interact with the output layer, right? An ANN is said to be fully connected. Okay, this is one type of neural network architecture. So it is said to be fully connected if every output from one layer connect to every neuron in the next layer, right? So you see that okay, a layer is that a group of neuron. Okay, this is why we group the neuron. We have this is the first layer, this is the second layer, and this is the third layer, right? And in this case, you have every neuron in one layer connect to every neuron in the next layer. This one here connect to that one, also that one, and also that one. Okay, and this one here connect to this one, that one, and that one. So each neuron connect to every neuron of the next layer. So in that case, you have that you have a fully connected neural network. Okay. An ANN is said to be a feed-forward network. Okay, this is just the way we we define different type of architecture. So a feed-forward network, if none of the output of one node is the input of another node of the same or a previous layer. Okay. So you can see from the connection point of view between the neuron in the neural network of feed-forward network, right? You see that every neuron has connection to neuron in the next layer, right? So you have no connection to the neuron in the same or in previous layer. If you have the connection from this one to this one in the same layer, then this one is not a feed-forward network, right? Or if you have connection from this one, go back to the other one in the previous layer, then again, this is not a feed-forward neural network, okay? This is just a definition, right? Okay, nothing too important. When a node output backlink as input to a node in the same or previous layer, it is a feedback network, right? Okay, so if you have connection from this one to this one, then okay, that is not a feed-forward, but it's a feedback network. Okay, or you have connection from this one to the one in the previous layer. It can not only the one behind, but the one further behind. Okay, then this is a feedback network. Okay, and if the feedback network is the input link for the node in the same layer, then it's a lateral feedback. Okay, so if you have the connection from the node within the layer, then it is lateral feedback. If you have the feedback with closed loop, and in this case you have recurrent neural network. Okay, closed loop mean okay, you have a connection from this one to this one. Okay, then you have from this one to that one. Okay, then you see it is recurrent neural network. This is the example for the feed-forward. The connection between the unit do not form a direct cycle, right? Okay, the connection is just from the left to the right. Okay, for the recurrent neural network, you have the connection from a direct cycle. Okay, you have the information, the signal coming from this one to this one, go to here, and then you output, and the output out to here, but also going back, and then on the way it's going back. Okay, it will continue and making a loop. Okay, a direct cycle. For the neural network, you can have a network with a very small number of layers, but it will also have a network that can have multiple, a very deep network, right? The idea is if you have a very deep network, right, then you can then you can learn and then you can how to say then you can had the same learning capability with a smaller number of parameter of neural network parameter. Let me explain to you more clearly. Okay, so it says that a neural network can represent any function if it is wide enough. Y is talking about the size of neuron in the layer, right? The number of neuron in a layer is not enough and deep enough, right? A neural network can represent any function, right? So if you want to reduce the depth of the network, right, then you will have to compensate by increase the width to a power of times. So that means that if you want to reduce the depth, then you will have an exponential increment in terms of the width of the network. Okay, but if you have a multiple layer network, right, then you will need far fewer neurons, then fewer learning parameter than a network with a very big width, okay, to be represent the same function, right? So let's say that there are two things that refer to the size of the network, the width and the depth, right? If you have a shallow network, then for the same purpose, you will have the very big width network, okay? But if you want to reduce, if you increase the number of layer, then you will have a deep network that for that network it is a lot smaller in terms of number of neuron, and it can represent the same function at the very wide very shallow network. So this is an example of function approximation with the neural network. So in the figure you have here, it is a function, and actually we can approximate that function by a combination of several ReLU function, right? So ReLU is the activation, and then the net input, right? And you see you can divide the function in different parts, and each part will be approximated by a ReLU function. Then you see that, okay, it is the function that can easily approximate the function you want. Okay. So the theorem that say any bounded continuous function can be learned by an INN using one hidden layer is described in the paper by Sabenko 1989, and the other paper in 1991. Okay, anything to say? Do you have any question? If you have no questions, then I suggest that we take a 10-minute break. Okay, and then we will be back at 5 to 14. Okay. Okay, so let's continue our lesson. So now we discuss the different type of neural network learning. Basically, in neural network, you have two type learning. One is parameter learning, and the other one is structure learning. In parameter learning, the idea is to adaptively train the weight of the connection in the neural network so that it will make up the final model. So for that learning, you do nothing with the, sorry, it's not, so for that learning, you somehow fix, you somehow describe the network architecture, a fixed network architecture. And then the idea is to learn the weight of the neuron connection in that network architecture. Okay. In structured learning, the goal is to adaptively train the network structure, including the number of neurons and the type of connection between them. So you see here is the image that represent the structured learning. For example, after the training or during the training, the neural network architecture train, right? For example, it can drop the connection from this neuron to this neuron, right? Okay. These two type learning can be done simultaneously or separately. And in most of the case, we will only consider parameter learning. And it is more popular type learning when we discuss about training neural network. So let me tell you again that for this parameter learning, you start with the neural network architecture. You start with this specific neural network configuration with this number of layer, this number of connection, right? And the idea is to learn the weight that describes the connection between the input and the input layer, and then the input layer to the hidden layer, and between the hidden layer and the hidden layer and the output layer. Okay. In principle, when you train the neural network, the approach is to first define the loss function. The loss function is also called as the error function. And basically, you want to find out the network connection and the weight of the connection between the neuron in order to minimize the error, right? You really want that, okay, with that specific sample X, and the output after the network is very similar, close, or the same as the expected Y. Okay, so the learning methods of neural network can be gradient descent with backpropagation of the error. We will discuss about this in the next slide. So yes, so in this figure, what you see here is the hyperplane of the arrow, right? With the different parameter of the function j. J is the loss function, the arrow function. All right, and this this is the hyperplane of the J function, and you have two parameters, for example, the theta 0 and theta 1. And actually, you want to minimize the J function, and it really means that you want to find out the lowest point in the hyperplane. Right? Let's say this is the optimal point. Okay. So the idea of gradient descent, right, is to go from the initial state in the hyperplane, and you somehow go down, right, and to the optimal point, right, to have the minimal value for the J. Okay, and if J is minimal, then you mean that that means that you minimize the error between the expected output and the output of the network. Okay, and backpropagation. Okay, this is a mechanism. You propagate the error from the output of the network and go back to the output layer, hidden layer, and then the input layer, right? That means you move back the error, and then you calculate the you calculate the how to say the contribution of each weight, like neuron, to the arrow, right? And then you can minimize that contribution. Okay. Okay, for the loss function, depend on different problem, that different challenge, different setup. You might have different loss function. It really depends on the objective, right? Here I want to show you a very simple loss function. Consider an ANN with n output neuron. Okay, for learning example, X and D. Okay, X is the input signal and D is the label. Okay, the value of the training error caused by the current weight vector W is calculated as follow. It's this formula. So this is like the square of the differences between the expected output and the output. Okay, you do the weighted sum for every output neuron from 1 to n. Okay. Okay, so this is a formula for the error caused by the current weight vector for one specific learning example, XD. And if you want to calculate the learning error caused by the current weight vector for the entire learning set D, then you do the sum, right? So the learning error is this one over the number of learning sample, right? And the sum of the error for every sample. Okay. So in order to minimize the error with the gradient descent, then here I show you about the gradient of E, right? The gradient of E denoted as delta E. It is a vector of multiple components. So x component is a partial derivative of E over a particular weight in the neural network. Okay. So in this case, we have the n is a total number of weight in the network. Right. So actually, the gradient vector of E will be a vector of n component. X is a partial derivative of E over a specific weight. Okay, so by definition, the gradient delta E will determine the direction. It determines the direction that causes the fastest increase in the error value E. Right. So, for example, we have a very simple function. Okay, this is parabolic function. Let's say at this specific point, right? Then this is the gradient. Okay. Then the gradient causes the fastest increase in the error value E. Okay. So in order to minimize, you should go into opposite direction. The direction that causes the fastest decrease is a direction that is opposite to the gradient of E. That means you should go the other way. Okay. So the delta W is minus. Sorry, this symbol. What is the name of this symbol? Let me check. Correct symbol. Eta. Okay. Right. Eta. I'm too bad at correct symbol. Okay. So the delta W is minus eta dot delta E W. Okay. So actually it is okay. So this is for the for every weight, right? And for a specific weight, it will be the minus eta partial derivative of E over that specific weight WE. Okay. So of course, I mean, in order to update the weight this way, the activation function used in the network must have a continuous derivative, because actually you do the derivative of error over the weight. Okay. Okay, so this is an example of gradient descent. You have the error function is this curve, right? Let's say this specific curve, right? Okay, then of course, I mean, this is the direction of the gradient. Okay, and you go the opposite direction, you go here, right? Okay, you update the weight, and somehow after the update, the arrow you have is somewhere here, and then you go again, and at some point you might go to the minimum. Okay, and for example, this is another example. You are somewhere here, right? You go to the opposite direction to the gradient, and you do this iteratively, and somehow you will go to the minimum. Okay, so now we will go into detail the backpropagation algorithm. Do I have any questions so far? Hello. Okay, so I should move on. Backpropagation algorithm. A multi-layer neural network learned by the backpropagation algorithm can represent a highly nonlinear separation function. To minimize the error, the difference between the actual output value and the desired output value for the learning example, we can use a backpropagation learning algorithm. Actually, the algorithm will help us to learn the weight of a multi-layer neural network. That means that in this situation, we have parameter learning set up where we have fixed network structure. The neuron and link between them are fixed, right? And for each neuron, the activation function must have a continuous derivative, something we discussed before, okay? And the BP algorithm apply the gradient descent strategy in the weight update group. So that is the idea of backpropagation. I need to correct the slide a bit. So activation. Okay. Somehow. I can, let's delete this to make things clearer. Okay. Sorry, not here. Okay. Right. Better to just delete it. Okay. Okay, so the idea of backpropagation learning algorithm is to search for a vector of weight that minimize the overall system error for the training set. Okay. So the backpropagation algorithm consists of two stages, senior forward state and backward propagation of error state. So in the senior forward state, the input senior, which is a vector of input value, are propagated forward from the input layer to the output layer. The code is passed through the hidden layer. Okay. And in the backward propagation of error, based on the desired output value of the input vector, the system will calculate the error value. And starting from the output layer, the error value is propagated back to the network from layer to layer until the input layer. And the error backpropagation is done by calculating recursively the local gradient of a neuron. Okay, so that is the idea of backpropagation. So let me remind you again that it is two phase, two stages. First stage is senior forward. So you put the input sample at the input layer of the neural network, and then you forward that senior to have the output, right? So okay, so that's the end of the senior forward stage. In the backward propagation of the error, you compare, okay, so okay, not compare, but you really calculate the error based on the expected output and the output of the network, right? And then you start from the output layer, you propagate the error back through the network from layer to layer until the input layer, right? So this is in opposite direction to the forward state, right? And the error back propagation for neuron is done by calculate the local gradient of each neuron. Okay, we have the figure for this back propagation in this visualization. This is a senior propagation test. Okay, so this state activate transmits the signal over the network, right? In the error back propagation state, the output error is calculated, and then it is propagated back to the through the network, right, from the output to the input. Okay. Okay, so we have the exam for you to understand clearly the back propagation, how the algorithm work. This is somehow similar to the exam that you have in the neural network lesson in the machine learning course. So you are given a 3-layer network in the figure we have here, and we have m number of input signal, right? Xj, j from 1 to m. Okay, you have L number of neurons in the hidden layer, ZQ, Q from 1 to L. You have N number of neurons in the output layer, YI, I from 1 to N. You have W, QJ, okay, WQJ, okay, see here. Okay, so it is a weight of the connection from the input signal Xj to the neuron in the hidden layer ZQ. Okay, you have WIQ. It is the weight of the connection from the neuron in the hidden layer ZQ to the neuron in the output layer YI. Output Q is the output, the local output, right? You have many output. It is a local output. You have the local output of the neuron in the hidden layer ZQ. The out I, it is the output of the network of the neuron of the output layer YI. Okay, is that okay for the definition? Okay, so for training sample X, you have the input vector X, right? And the input vector is propagated from the input to the output layer. The network will produce an actual output value out. That is a vector of Li. I is from 1 to n. Okay, that is clear. For an input vector X, a neuron ZQ in the hidden layer receives the overall net input. Okay, this is nothing, I mean, different. Okay, so this is the ZQ receives the net input, and then this ZQ will produce an output locally, and that is equal to this formula. Okay, so F is the active activation function of the neuron ZQ, right? Okay, this is a function over the receive net input. Okay, and okay, this is also in the forward propagation stage. The overall net input of the neuron yi in the output layer. So actually it is the net input sum, weighted sum of WIQ and LQ for Q from 1 to L. Okay, and if you replace the LQ somewhere here, you will have the weighted sum of WIQ and F, and then inside you have the weighted sum from WQZ and XZ. Okay, and this neuron YI produce an output, and this is a formulation for the output, right? Nothing difficult. Okay, the vector of Li for I from 1 to n is the actual output value of the network given the input vector x, right? This is correct, right, and clear, right? Okay, now move to the next stage, backpropagation. For chaining sample x, the error signal due to the difference between the expected output value d and the actual output value L are calculated, right? And the error signal, I mean the way we calculate will be depend on the loss function, right? The error signal are backpropagate from the output layer to the input layer, and in order to update the weight, right? We define our error function is that square error. Okay, this is the definition of our error function. Why? Nothing difficult. Okay. Okay. Any question? Any question? If you have no questions, so please turn off your mic. Okay. So now we apply the gradient descent method in order to update the weight, right? The weight of the link, the connection from the hidden layer to the output layer are updated by this formula, right? The delta WIQ equal to minus eta partial derivative of E over WIQ, right? And we have the derivative chain rule for this, partial derivative calculation, so that the delta WIQ will be minus eta, the partial derivative of E over the Li, right? And then the derivative, partial derivative of Li over the net I, and then partial derivative of net I over the WIQ. Because actually E is a function of Li, and Li is a function of net I, and net I is function of WIQ. So this way you have the derivative chain rule like this one. Okay. And if you compact the formulation, you will have the eta and then di minus the Li, right? And then the derivative of the activation function f, right? And then the out q, and actually the eta multiple with the, what is this symbol? Not symbol. Delta. Okay, so it's eta, delta, and out q. Okay. The delta I is the arrow signal of the neuron yi in the output layer. Okay. And this is the formulation for the delta I. Okay. So now you know how to update the weight of the connection from the hidden layer to the output layer, right? We know how to update this WIQ, right? Now we will find out the way to update the WQJ, okay? To update the weight of the links from the input layer to the hidden layer, we also apply the gradient descent method and the derivative chain rule. And this is formulation for us to update the WQJ, the delta WQJ equal to minus eta partial derivative of E over WQJ. And it is actually this way by application of the derivative chain rule. Okay. And from the formula for calculating the arrow function E, we see that arrow component is a function of out q, right? And it is the E, right? The arrow function. And applying the derivative chain rule, we have the delta WQJ is actually equal to eta and the sum of delta I WIQ for I and derivative of f net q and xj for I range from 1 to n. And we can refine the formulation by the definition of delta q is the arrow signal of the neural network ZQ of the hidden layer, and ZQ is this formulation. Okay, and in that formulation, the net Q is the net input of the neuron ZQ of the hidden layer, right? And the derivative of f on net Q is derivative of f net Q over net Q. Okay. So according to the above formula for calculating the arrow signal delta I and delta Q, the arrow signal of a neuron in the hidden layer is different from the arrow signal of a neuron in the output layer. Because of this difference, the weight update procedure in the backpropagation algorithm is also known as the serialized delta learning rule. So the arrow senior delta Q of the neuron ZQ of the hidden layer is determined by the arrow senior delta I of the neuron YI of the output layer. And that was a neuron ZQ connect to. And also it is determined by the coefficient we got the weight WIQ. So I have just introduced to you the backpropagation algorithm on a very small neural network consists of the 3 layers, 1 input layer, 1 hidden layer, and 1 output layer. So this the process of course can be easily extended derived to neural network with more than 1 hidden layer. The general form of the weight update rule in the backpropagation algorithm is as follows. The delta WAB equal to eta delta A XB. So the eta is a learning rate, right? And B and A is a 2 indices corresponding to the 2 ends of the link from base to E, from a neural network or input signal B to the neuron A. XB is the output value of the hidden layer neuron or input signal B, and delta A is the arrow signal of the neuron A. Okay, so any question? Hello. Okay, so we can move to the procedural course of the backpropagation algorithm. So we have the neural network consist of a Q layer for Q from 1 to upper Q. Okay, we had QNet I and QNet RI as the net input and the output of the neuron I of the layer Q. Okay, and ZM is the number of inputs and Zn is the number of outputs of the neuron network. The QWIJ is the weight of the link or the connection from the neuron J of the layer Q minus 1 to the neuron I of the neuron Q. Okay, so this is our definition. Okay. Okay, so the backpropagation algorithm will run several states. In the state number 0, it is initialization, right? So in this initialization, we should initialize the weight, right? We should start with some initial value for the weight, right? Because for the backpropagation, we will update the weight, right? For the updation, we need to know the previous value of the weight, right? So we can just initialize the weight with some specific random value. We also select the threshold for the arrow. Let's name it E threshold, the acceptable arrow value. And this threshold will be used for us to stop the iteration. And also we set the arrow to be 0. We haven't do any computation for the arrow. Okay. So let's move to the next step. So in this step, we start learning epochs. Okay, so the concept of epoch is It's one iteration where you have used all of the training sample for the training. Okay, so in step 1, you apply the input vector of the learning example key to the input layer. Of course, for the input layer, q is equal to 1, and then you have the qri equal to xi k. Okay, this is just say that okay, you want to put one example to the input of the network. Okay, and then you do forward propagation. You propagate the input signal through the network until the network output value are received. And of course, you receive the output at the output layer QRI. Okay. This is the formulation for calculating the QRI. Right. So in order to, it is like the activation and then the net sum, the net input. Okay. And of course, the net input is the weighted sum of the weight in the previous layer with the output of that previous layer. Okay. Okay, so in the step 3, you calculate the output error of the network, and the error signal delta, the Q delta J. Okay, sorry, the Q delta I, sorry, a big neuron in the output layer. Okay, and this is a formulation for the Q delta I. And then in the step number 4, you do the arrow backpropagation. The arrow backpropagation to update the weight and compute the arrow signal Q-1 delta I for the prior layer. And this is the formulation that I showed you in the previous slide when we do the demonstration for that small network, right? In the step 5, you check the end of a learning cycle, an epoch. You check if the entire learning set has been used. One learning cycle done, then it is one epoch, right? If the entire learning set has been used, then you go to the step number 6. Otherwise, you go to step number 1 to start with another example, right? So at step number 6, you check the overall error. If the overall error E is less than the acceptable error threshold, that was something that you defined before in the step number 0. And if it is satisfied, then the learning end and the learner weight are returned. Otherwise, you reassign the E equal to 0 and you start a new learning cycle. You return to step 1 and the epoch will be increased. Okay. So in this procedural code, you actually use the threshold at the as a stopping condition. In reality, you may use the number of epoch as the condition to stop. Let's say you can do a for loop from epoch number 1 to 200, and this after the 200 you stop. Okay. Okay, so we have initiation for the backpropagation algorithm. This is a forward propagation. You can do you fetch the input, right? And then you calculate the out for the neuron 1, the out for the neuron 2, and the out for the neuron 3, okay, and then you calculate the output for the neuron 4 and the output for the neuron 5, and then you do the calculation for the output for the neuron number 6, okay, and then you calculate the error signal for the neuron 6, right, with the expected output value and the output of the network, right? So that's the formulation for calculate the delta error, the error signal for the neuron 6. Okay, and from that you can just move back and then you can calculate the delta error, the error signal for the neuron 4, and then the error signal for the neuron 5, and then error signal for neuron number 1 and number 2 and then number 3, okay, and with that delta error you can do the weight update. So of course the weight will be the previous weight in the previous iteration minus the or plus the eta and then the delta I and x once, right, for the first first component of the input, okay, and then you can update the weight 1 x2, right, this one here from the previous value, and then we plus with the eta delta 1 x2, okay, so eta is the learning rate. Also the same for the W2x1, W2x2, and also for the rest, okay. So in a backpropagation algorithm, you have to initialize the weight value, right? And usually the weight are initialized with small random value. If the weight have large initial value, then for some activation, such as for the sigmoid function, that will reach saturation early, and this is a sigmoid, okay, right? And if the weight is too big, then the output after the sigmoid function will be somewhere in here, and it is says that at this situation you have a saturated neuron, and at this point the gradient will be 0 because you have a flat curve here, okay. The system will store at a saddle or a stationary point. That means that somehow you let me draw the saddle point. For example, this is a curve of the arrow hyperplane. Sorry, I cannot write it very clearly in high dimension, but you see this is, say this is a stationary point. For example, in this case the gradient is 0, so that if it's 0, then you cannot update the weight, okay. So if you cannot update the weight, then the system cannot learn, okay. Okay, I forgot to translate this slide. Okay, so learning rates also have important impact to the backpropagation conversion. If you have the eta, the learning rate is too big, then the updation will be big, right? Because you see the eta in the updation formulation. Okay, if it's big, then okay, the update will be big. Okay, so it will have the it will have the learning to be very fast, then because for every step you will go with a big step, right? But somehow it might lead to the fact that it cannot lead the model to the optimal, because if you move too fast, then you might, jump over the optimal, right? You cannot jump to the optimal, right? If you have the eta to be too small, then the learning process will be too long, right? I think that I have the figure for you. No. Okay. Let's go with the figure in here. Right. So assume that at the initial step, you initialize the weight and the arrow is somewhere here. Okay. Then you do the back propagation and you update the weight. If you have the high learning rate, then maybe for each step you can move fast. You can move to this point, you can move to this point, and you can move to this point. And somehow you cannot, go to the optimum because you move too fast, right? You jump from this position to other position and cannot jump to the optimal. If you move too slow due to the very small learning rate, and you see, you go very carefully, and it took very lot of time for the model to be converged to the optimal. Okay. Anything to discuss about? Okay, so in reality, usually for the learning rate, you will choose the learning rate by experiment, right? By your experience and her experiment, and it really specific to different problem and different data sets. The good value for the learning rate in the initial epoch might not be good in the after epoch, right? So maybe it is a good strategy to have adaptive learning rate, something we will discuss in the next lesson. Okay, here we discuss the number of neurons in the hidden layer in the backpropagation algorithm. The size of the hidden layer is an important question for the application of multiple layer neural network to solve the real-world problem, right? In practice, it is difficult to determine the exact number of neurons required to achieve a desired system accuracy. So I just want to say that the number of neurons for a hidden layer is somehow cannot be determined exactly the optimal value for the number of neurons in the hidden layer. So, and also, as the learning rate, you choose the size of the hidden layer by experiment, trial and test. Okay, so here I show you some variants of a gradient descent algorithm. So for gradient descent algorithm, you start with the initial learning rate, and you compute the loss, the error signal for every example in the training set, right? And then you update the weight, right? And you repeat the step number 2 and 3 until conversion. In stochastic gradient descent, you initialize the weight W, and you compute the loss according to each particular exam, right? And then you update the weight. Okay, so difference is this: here you update the weight right after and for every example, right? And here you update the weight after you consider every example in the training set. In mini-batch gradient descent, usually you update the weight, and you calculate the loss here for a batch, for example a batch size of n sample, right? And usually in practice, you use mini-batch gradient descent for the updation at the iteration. Gradient descent go in the steepest descent direction, but slower. Why slower? Because you need to calculate the the error signal, the average error signal for every sample in the training set, right? So that it will be slow, but because you consider every sample in the training set, then the direction you move will be the steepest descent direction, right? In stochastic gradient descent, it is faster because you just calculate the error signal for each sample, and then you update the weight, right? It's faster, but it somehow does not follow the steepest path, so it can move, flexible a little bit, right? Okay, and for the mini batch stochastic gradient descent, it's like in the middle, right? Okay, so in summarize, the pros of ANN is it mimics the natural structure of natural neural network in our brain, and it supports a high degree of parallelism. It have good performance in many problems and many different data types, such as photo, video, audio, and text. It is very flexible in terms of neural network. You can see in the next lesson for this kind of popular network architecture. And the deep learning allows us to automatically extracting the feature from the data. That means that now, as the deep learning engineer, we don't need to care too much on the feature engineering. We can just take a bunch of data and put the data into the network, and then we can learn and output a model with high performance. Right. So it's very much different to traditional machine learning method. In traditional machine learning method, the performance of the overall model depend very much on the manual feature engineering, feature extraction, and experience of the engineer. And now that hard part is not important anymore if you use a deep learning approach. But I mean, the concept of the ANN is the fact that you need to have a lot of data, and there is no zero rule to determine the optimal network structure and some hyperparameters such as the learning rate, right? There is no zero method to evaluate the inner working of ANN. So that the ANN system is usually seen as the black box. And it's also very difficult and impossible to give an explanation to the user. Nowadays, people are working a lot on explainability of machine learning model. And you will see that even for the neural network, we have the way to describe how the network learn from our data, how the network make the decision from the data. The other disadvantages of neural network is about the theoretical foundation. There is little theoretical foundation to help explain the success in practice. Okay, you apply ANN when the form of the learning function is not known in advance, when it is not necessary or not important to provide an explanation to the user, or you accept a long time for the training process. And when you have the possibility to collect a large number of learning data, it is important because for the neural network, usually you have a very, very big number of parameters to learn, right? You can have a network with 100 million learning parameter. And for that big parameter to learn, you need to have a lot of data. Okay, and in the practice, a lot of ANN has been deployed for different data types, such as image, video, speech, and text, and they got a very good performance. So, of course, I mean, if you have an image, video, speech, and text, you might consider ANN as well. Okay, so this is something I discussed in the first part of the lesson, but maybe it's better to discuss it here after the introduction to the neural network. You have hardware, the GPU, it have massive number of core, and with the massive number of core, it can process the neural network computation in parallel. So you see that for the neural network, it will be easy for you to do the calculation in parallel, right? For every neuron in each layer, you can do the independent computation, and they can be done in parallel. Yes, okay, the software, PyTorch or TensorFlow, whatever. You have big data so that it can train big network. If you have big network but you have no data, then there's no way for you to learn a neural network from scratch. Or I'm not talking about transfer learning or some, I mean, recent learning mechanism, but I'm talking about training a neural network from scratch. If it is the case, then you need big data. Okay, some open library, Keras, TensorFlow, PyTorch, Caffe, and representation. Do I have any question? Okay, so if you have no question, okay, then I think that we can stop here, and we will meet again in the next week. And thank you. Bye bye.